Picture this. It's the 1990s. We're right in the middle of the absolute golden era of Japanese performance. And today, we're looking at two downright legendary, lightweight, three-door hatchbacks. We've got the EG generation Honda Civic SIR, and we've got the Mitsubishi Mirage Cyborg R. Both of these machines are packing 1.6-liter four-cylinder engines. There are no turbochargers here, no superchargers, no massive displacement. Yet both of these engines are completely world famous for screaming to unbelievably high RPMs, delivering this raw driving experience that enthusiasts are literally still chasing today. So, okay, let's dive into this. Here's our central engineering mystery for today's explainer, and it is a fascinating one. If these two power plants are so incredibly similar on a fundamental level, how on earth did Honda and Mitsubishi take completely different mechanical routes to make them breathe? We aren't just going to sit here and read spec sheets today. We're going to unpack exactly how these brilliant engineering teams solved the exact same physics problem, but used completely different mechanical languages to do it. Look, on paper, the B16A and the 4G92 are eerily similar. They both use a 1.6-liter inline-4 layout, they both rock dual overhead cams with 16 valves, and they're both naturally aspirated, high-revving masterpieces. But here's the thing. Numbers alone absolutely do not explain why these specific high-performance Japanese market versions feel so totally unique from behind the wheel. To really get that, we have to look way past the stat sheet and deep into the cylinder head. Because honestly, generating massive, high RPM horsepower from just 1.6 liters of displacement, that is an absolute engineering marvel. When you don't have the luxury of a giant engine block, you have to look at the engine fundamentally for what it is, an air pump. The more air and fuel you can efficiently pump through that tiny 1.6-liter space in a given minute, the more power you're going to make. And that brings us to engine breathing. Basically, this is the mechanical process of drawing air in through the intake valves, mixing it with fuel, igniting that mixture, and then forcefully pushing it out the exhaust valves. And here is where things get really tricky. Valve lift, which is how far the valve opens, valve duration, how long it stays open, and valve timing, exactly when it opens. All of these become incredibly, absolutely crucial as RPMs rise. Why? Because at high speeds, this little 1.6-liter air pump is frantically trying to breathe thousands of times every single minute. To put that into perspective, right around 8,000 RPM, those valves are opening and closing over 60 times a second. Imagine trying to breathe through a tiny little straw while sprinting as fast as you can. That's the ultimate high RPM compromise for an engine designer. A camshaft profile perfectly optimized for smooth, low RPM street driving, well, it heavily restricts airflow at high speeds. It's exactly like breathing through that straw. But if you just throw in an aggressive high RPM camshaft to let the engine gulp air at 7,000 RPM, it completely ruins the low-end behavior. The car is going to idle poorly and just stumble around town. Variable valve technology exists specifically to eliminate this compromise. Honda's solution: inside VTEC. So Honda's core philosophy with the B16A was to dramatically change the engine's breathing characteristics right as it approaches those upper RPM limits. They wanted a perfectly well-behaved street car at 3,000 RPM and an absolute track monster at 7,000 RPM. And here is how they actually pulled it off. As the engine RPM increases, the ECU, the computer, is constantly monitoring engine load, speed, you name it. At the exact right moment, it commands hydraulic oil pressure to flow right into the rocker mechanism. This pressure forcefully pushes a set of locking pins into place. Now, it's super vital to note here, VTEC doesn't physically swap out the entire camshaft. Instead, those locking pins bind the rocker arms together, forcing the valves to suddenly follow a completely different, high-performance central cam lobe. And this brilliantly illustrates that the famous VTEC kick you always hear about isn't some sort of electronic trick or magic. It's a visceral, physical transition in valve operation. The valves are suddenly opening further, they're staying open longer, you get this massive surge in cylinder airflow, a dramatic, super aggressive change in the induction sound, and a power curve that steeply rises right when a normal engine would be totally running out of breath. Mitsubishi's answer: inside MIVEC. Now, what's really interesting about this is how perfectly these two approaches contrast. Let's cross the Pacific for a second. Mitsubishi engineers were looking at the exact same breathing problem for their Mirage Cyborg R, but they didn't just copy Honda's recipe. No way. They developed the 4G92 engine using their very own distinct architecture. While Honda's VTEC uses that multi-lobe locking pin design for a super dramatic, sudden personality change, the MIVEC implementation utilizes a completely distinct mechanical rocker and follower strategy. Mitsubishi's goal was similarly to alter valve lift and timing, sure, but their mechanical architecture was uniquely their own. They optimized breathing as the revs climbed using a completely different mechanical linkage strategy. Power equals torque multiplied by RPM. So the crucial point here is understanding the physics behind why this even matters in the first place. You see, a small displacement 1.6-liter engine naturally lacks the massive low-end torque of, say, a big V8. Therefore, the only way it can make big horsepower is if it can maintain useful torque at incredibly high engine speeds. And to maintain that torque at 7,000 or 8,000 RPM, it all comes down to the cylinder head battle. Both the B16A and the 4G92 rely heavily on massive airflow efficiency. The engineers had to perfectly sculpt the intake ports to pull air in rapidly, design precise combustion chambers to burn it flawlessly, and route exhaust headers to scavenge those spent gases right out. The variable valve systems, they merely unlock the potential of these beautifully engineered cylinder heads. And that potential is also heavily dictated by the engine's internal geometry, specifically the bore and the stroke. The bore is the width of the cylinder, and the stroke is how far the piston travels up and down. To get that high RPM horsepower, the pistons in these engines are traveling up and down so fast that their peak speed actually rivals Formula One cars from the exact same era. Crazy, right? These dimensions force engineers into a really tough balancing act. A wider bore allows for larger valves to move way more air, and a shorter stroke keeps piston speeds safe at high RPMs. But you often have to sacrifice that off-the-line, low-end torque to get it. And man, when all of this perfectly calculated geometry and variable valve timing come together right at the top of the tachometer, you get that famous spine-tingling sound. A lot of people actually think the variable valve system itself makes a mechanical click that you can hear from the cabin. It doesn't. That dramatic screaming sound is actually the acoustic explosion of the new aggressive valve motion, allowing massive amounts of air to suddenly rush through the intake resonance chamber. All of that is combined with the rapid-fire exhaust pulses of an engine spinning thousands and thousands of times a minute. The driver's seat. All right, let's pivot from the engineering dyno over to the driver's seat. Because ultimately, you don't drive a spec sheet, right? And you definitely don't drive an engine block sitting on a test stand. You drive a car. And how these engines actually feel is heavily influenced by the chassis they're bolted into. When you drop the B16A into that lightweight EG Civic platform, or the 4G92 into the Mirage Cyborg R, everything is amplified. These cars featured beautifully optimized power-to-weight ratios, incredibly sharp throttle responses, and crucially aggressive short gearing. That short gearing means the engine revs up incredibly fast, meaning you get into that high RPM variable valve sweet spot way quicker and you stay there longer. The car's physical makeup is what turns a great engine into an unforgettable driving experience. Which naturally leads us to a fascinating question. If Honda and Mitsubishi were both trying to solve the exact same physics problem, getting a 1.6-liter naturally aspirated engine to breathe at high RPM, why on earth didn't these two genius engineering teams just build the exact same mechanical system? Well, the answer is that automotive engineering is just a massive, complex web. It's not just about what works best in a vacuum. It's about complex patent protections that actively prevent copying. It's about working within existing engine architectures to keep manufacturing costs down. It's about the historical expertise of the specific engineers at each company, and of course, their distinct brand performance goals. So multiple brilliant mechanical solutions can and absolutely do exist for the exact same problem. Two philosophies, one goal. Ultimately, what we're looking at here are two differing philosophies aimed at a single unified goal. And impartially speaking, both the Honda B16A and the Mitsubishi 4G92 MIVEC wildly succeeded. They both answered that fundamental engineering question of how to make a small displacement engine breathe effortlessly at its absolute limit. They completely redefined what a four-cylinder compact car was even capable of. To wrap up this explainer, I think this quote captures it perfectly. One became famous for the moment VTEC changed the engine's personality, the other proved that Mitsubishi could play the same high RPM game with its own mechanical language. We really don't have to declare a simplistic winner here. We can just celebrate both of these 1990s masterpieces for the sheer engineering brilliance they brought to the road. So I'll leave you with this to think about. Knowing how they both tackle the physics of airflow and understanding the sheer mechanical genius behind the locking pins and the rocker assemblies, which mechanical language speaks to you? Are you all about the sudden, dramatic kick of Honda's VTEC or the unique high-revving architecture of Mitsubishi's MIVEC? Keep exploring, keep learning, and I really hope this explainer sheds some light on what makes these 1.6-liter legends truly tick.